A great event is graced by great personalities. Great leaders don't just create followers, they create more leaders. I request Dr. R. Praveena, Assistant Professor, to introduce the speaker of today.
It is my honor to introduce Dr. K. Palpandi, Assistant Professor in the Department of Mathematics, National Institute of Technology, Calicut, Kerala. Dr. Palpandi obtained his PhD in Mathematics from Indian Institute of Technology, Madras. His area of specialization include linear algebra and optimization, where he has made remarkable contribution through his research. Sir has an impressive record of publications in reputed international journals. His works on tensor complementarity problems, linear transformations, and matrix theory are widely cited and appreciated in the mathematical research community. He has delivered invited talks and lectures at several institutions, with rich teaching experience across premier institutes such as NIT Andhra Pradesh, MNIT Jaipur, and NIT Calicut. Sir is also the recipient of several honors, including qualifying CSIR JRF, AIR 34, and GATE in mathematics, along with multiple academic distinctions during his school and college education. We are truly privileged to have him with us today as our resource person for this faculty development program. Welcome you, sir.
Thank you, ma'am.
Yes.
Knowledge is love and light and vision. Wisdom is knowing what to do next. Skill is knowing how to do it. And virtue is doing it. I request Dr. R. Palpandi, Assistant Professor, Department of Mathematics, NIT Calicut, Kerala, to take over the session.
Yeah, thank you so much, ma'am. And also thanks, Praveena Madam, for nice introduction. And also thanks, Praveena Madam, for inviting me as a resource person. Okay, I will start talk. Before that, I will share my window. Please confirm that whether my windows is visible or not.
Yes, sir.
1 minute. One minute, ma'am. Actually, I am trying to share it, but I am not able to do it.
Yes, sir. No issues, sir. Yes, sir.
Okay. Ma'am, actually, that one more account I joined, Palpandi K. Can you make it the presenter or something? I joined actually through the two account. One is Dr. K. Palpandi, another Palpandi, another one is Palpandi K. Can you make it as
Yes.
a Palpandi K as a presenter so that I will?
Yes, sir. RK, sir.
Already we make it, sir. So?
Yes, sir. Yes, sir.
So already I make it, sir.
Oh, okay. Even mics also I am not able to. I'm not able to do it.
So can you please join once again, sir?
Okay, sir. I will leave and I will join.
Okay.
Can leave. Sir, I am joining. Actually, you can allow me. Someone will let you in shortly. It is
Okay,
coming.
okay.
Yes. Yeah, now actually you can make.
Sir, let me just.
Now I joined through that another one. You can make me as a presenter, sir. Right now
Okay.
there is no option is coming. Camera, mic, share option is not coming. Disable. Here also some issues there. And here share option is coming. Not one nota.
Palpandi, sir, is this working?
No, sir. Actually, it is not coming. One more device, sir, it is not coming. I planning to write it through that one only tablet, but it is not coming. I'm trying from another.
Should I have make two ID as a presenter, sir? But I.
Yeah. Two IDs I'm having. One more ID, it is not coming.
Yes, sir. Palpandi K and another one is
Palpandi K only.
Palpandi.
From there only, I'm trying to share it. It is option is coming, but I'm not able to. It is coming like that.
Okay, sir. Okay.
1 minute. I will.
Let me check, sir. Let me check.
Okay. Anyway, that I will try to join some another system, sir.
Okay, sir. Okay.
Okay.
Actually, both IDs are in a presenter mode, sir. But I don't know why in this happens.
Okay, sir. Anyway, I will try to join with her. Okay. My screen is visible, sir.
Yes, sir. It's visible now.
Yes, sir, it is visible, sir.
Okay. Actually, I have written in some other tablet. I have written everything. Anyway, it's fine. I will try to write it here.
Okay, sir. Okay, sir.
It's fine. Okay. Yeah. Okay. Sorry for the delay. Actually, I am not actually putting actually technical thing. Right. Okay, so good evening to all. Today, just I'm going to talk about principal component analysis. So this is one of the old technique. Okay, it is actually around 1930 to 40. This technique was founded actually, but it's frequently that recently actually a lot of modification of principal component analysis are there, and also we are using in many places we are using the principal component analysis. Okay. So this is a I will give the motivation why this principal component analysis are required. So see, mainly this is related to that machine learning. See, when we are giving that some data, this is actually a data set. So this data set actually in real life, this data set may generally it is very large. Okay. This data set may containing actually some noise or actually some unnecessary data also may be there. Maybe some data actually having actually the correlated data also may be there. See, these are the things may be there. Maybe actually some correlated data will be there, or some noise will be there. Okay. So this size of this data is very large. Okay. See, these are all the things may happen in the real life. When we are dealing with the real life data, this may be actually these are all things may happen. See, now what we are going to do here, we are going to give to the machine. Okay, to train the machine, we will give this data to the machine. Okay, then this machine trying to understand the data. Then after that, actually, they will try to understand actually the new things if you are giving. Mainly in the machine learning, unsupervised learning, we used to give the data, the machine will try to understand, will get the trained themselves, then try to identify the new things. So when we are giving this one, the machine actually what will happen actually if you are giving the large data, correlated data, the machine will take it a long time to understand the data. Our computational time of the data will be more. And also, due to the correlated and noise, this large one actually, the machine will actually get confusion also sometime. Okay. See, these are all the things may happen in the unsupervised learning. Whenever your data is very large, then actually these are all things may happen. Computational time, and also the even storage the data also, it will take time. Okay. So if you want to get it actually, if you want to give this data size, if you are reducing this data by keeping our important information without losing the important data, we would like to actually reduce the size of the data. When you are reducing the data of the data size, we have to keep it actually without losing any information. We should not actually lose the information. Otherwise, we cannot actually model a good model. We cannot make it without actually losing the information. So that is what we want to do it actually. That's what we want to actually get some method how one can reduce the large data into the smaller data such a way that we will retain all the important information such a way that actually we will get actually the correct model. Okay, so main thing is that we want to reduce the size. We generally used to call actually the dimension reduction. Dimensionality reduction. Okay, this is the motivation for the principal component analysis. Mainly what we want here, we would like to know actually what kind of mathematics involving here to reduce the larger data in the smaller size data. Smaller size data in the sense the higher dimensional data we are having actually higher dimensional data we are having into the lower dimensional data. When we are doing that time actually we have to retain all the information. Okay. So here how one can reduce the higher dimensional data into the lower dimensional data, we are having one technique that is called principal component analysis actually, that gives the method to reduce the higher dimensional data into the lower dimensional data, okay, by keeping all the original information in the new lower dimension also, right? So this is the motivation for actually principal component analysis. Okay, let me explain actually one simple example. We will take it. So, right. So I will consider this data set. Consider this data set for simplest case I am taking. We can take it. So suppose we are taking height and weight. So there are two features. Generally, we used to call actually these are all the called actually features. Features. So height of actually some n% you are you are finding that you are getting actually height will be 150 centimeters, maybe 160, and maybe 145, and 58. So weight, if I'm finding, that is I'm getting actually 40, 50. Suppose I'm getting actually 75. This is okay. This is actually suppose 50. Okay, suppose I'm having the data like I am considering having for 5% I'm having the height and weight of if you see this data, how this data is, you want to represent this data pictorially, so we need to see in the 2-dimensional, right? So if this I will take it as 8, x code x axis I will take it as 8, and I will take it's only 150 and 70 like that I'm having. So here I'm starting from maybe 40, 50, 60, 70, and 80. So this is 140. So 140. There is no 140. 145. I have 75. So I have the data like that. 75 and 150. I'm having actually that 40. 145 actually it is irrelevant. It will be 65. I will take it. The 150 I'm taking actually that 65. Okay. So then again actually 161. 161 I'm having actually 80. So 158 I'm getting actually 58. Around 58 I'm getting here. Anyway, this is the data I'm getting. One more actually 160 also I'm getting around 50. Right. So this is the data I'm having actually. Right. So this is the data I'm having. The 2-dimensional given data actually we are denoting the 2-dimensional. Okay. So now if I want to reduce into the 1-dimensional data, okay, then what one can do it? How one can actually reduce into the 1-dimensional data? Okay. Anyway, here we are having n is actually very less only, but it may not take actually much storage space. Now, if you want to reduce into the 1-dimensional representation of this given data, what we need to do, just actually look at actually this one. Look at actually this one. Just I'm going to draw the line. Okay, this already this data in the XY coordinate. Okay, if I draw the line actually like that, if I draw the line like that, so all data is actually near to this one, near to this line. Okay, near to this line. Maybe actually some more point also I am taking. One can actually I will take it some more points so that it can be understood easily. Okay, suppose in that case I am getting this line. Sometime actually I will get the other direction also I will get it. Suppose some point I am taking some more point also I am considering. So I will draw this line. Okay, this line such a way that all the points are near to this line. Okay. Anyway, I will tell later actually how one can find this line. Generally, this line we used to call actually the principal component. The principal component, first principal component and second principal component, like that actually we will find it. Okay, that's our main task is that higher dimensional data is given, how one can reduce into the lower dimensional data, how one can represent the data in the lower dimension. So key idea is that I will see that scattered of the all the points, then I will try to draw actually I will try to find one line which is very near to the all the points. Okay, very near to the all the points. So one can here one can observe this scatter point. You can see that how the heights variance of the height, how it is, how up to how it is varying. It is, you can see that this is a point actually the first point I am taking. This is varying actually here to here. The height actually the varies from this point to maybe this point. Okay, then that variance of the height, the variance of the height actually in this much. And look at actually how the y direction the variance is there. Data how varying in the y direction. One can find it actually from, I think this is largest. This is variance. Okay, this much it is varying. So height is actually in the x direction. Data points are varying actually here to here, and y direction data are varying here to here. Okay. So now actually, if I look at it, I have drawn this line. Okay, that is actually very nearest to all the points. Okay. So now you can see that along this line, how the data points are varying. Along this line, actually, how the data points are varying. So you can see that along the line, data points are actually varying from here to here. Okay, in this direction. And also, I will draw actually one more axis, which is actually perpendicular to this line. Okay, so this just we are changing the coordinate axis. Previously x and y are coordinate axis. Now we are finding actually new axis. Let's say u2 and u1. There are new two axes we are finding actually. u1 and u2 are actually orthogonal. Okay, so now you can see that the variance of the data in the u1 direction is more. Variance of the data in the u1 direction, you can see that here to here. But if you see that variance of the data in the x2 direction, it is actually we are getting actually very less. Okay, we are getting. So the variance of the data in the u1 direction is actually more, and the variance of the data in the u2 direction is more. Sorry, very less. It is point on the u1 direction only because of the variance of the data points in the u1 direction. It means that if I'm taking this one, actually it will give the almost all the information about the original data. That is a meaning. Okay. Anyway, I will do mathematically what is happening. I will derive it little later. But this is the idea. We need to find actually maybe we need to find the new coordinate axis such a way that each principal component actually we have to order it. Which principal component we are having the variance is more. Okay, you have to take that one u1, and also second one you have to take actually after that more variance, a little lesser variance you will see the another axis. That's the second principal component. Anyway, in that case, the two-dimensional data only two axes only the first principal component, second principal component only possibility. Okay, in that case, what I'm trying to say here, this data actually one can actually see on the line u1. Okay, if I write it actually this one roughly, if I'm writing, this is going to be, this is a u1 direction. All the data points are actually very near to this one, so I can say that actually this is actually reduced into the one dimensional. Your data is one dimensional. Take the projection on each point on the line. Okay, we will take the projection on each point on the line. Okay, that is going to be a new data set. Okay, the data set actually where we are denoting in the one dimensional. One dimensionally we are denoting here two dimensional data reduced into the one dimensional. Reduced into the one dimensional. So that is the idea. Anyone have any query about? Mathematically, I will try actually how I am calling this orthogonal projection, how I am telling this principal component we have to take it. Okay, so how it is going to give actually more information about the original data. So those things I will discuss later. So this is the idea. Okay, this idea, if we are having the data, that data may be have actually the correlated data also. Mainly would like to actually remove the correlated data, because the correlated data is actually going to give actually the same information only. So instead of actually two correlated data, it's better to take actually one correlated data. See, this process actually remove that actually correlated data, only it will keep that uncorrelated data only. Okay, in that way, if you are doing all the information, almost all the information will get from the original data, right? So anyone have any, please you can actually ask me. Okay, this is a simple example I have done. So one more thing we will look at. There is no. So I cannot see actually another window. I am in the. If any chart box is that, please the coordinator actually take care. You can tell me. I cannot see the that. So I'm coming to that another example, simple example I will consider actually. For example, actually you take this one also. So for example, one more things also I will tell actually why principal components are very important. Now take it actually this one picture I am taking. For example, any picture one can mathematically one can see as a pixel and one can treat as a matrices. Suppose I am having this picture, maybe I will take it actually, not put in drawing, but still I will try to this one. You take it as this is home. You take it this one. Okay. Here actually we are having, so this is a picture. Suppose it is 100 into 100 pixel. You are storing this one in the 100 cross 100 pixel actually. So now you can see that this data I want to store it. When I told actually the above one, what exactly we are doing actually that example, whenever you are having the correlated data, we want to remove it. Only we want to keep it as uncorrelated data only. That way one can reduce the dimension. That is the principal common analysis will do. Another one actually, that store a pictures. We want to actually store a image or something. In the quality also should not actually compromise. At the same time, actually we have to store the data in the smaller size. Because of actually we are having only limited space only. We cannot actually store actually a lot of things. Okay. So quality also we should not compromise. At the same time, actually we have to store in store the image or something in the less storage only we want to do it. So for that you look at this image actually, my concern here is a lot of unwanted data, unwanted things also there. That's what principal component analysis also will do. Any unwanted things, we know that what is the important feature. Here actually important feature, important things if you here this image if you are considering, our important thing is nothing but we want to store the image, not actually background. Background is not important. We want to store this image actually for some purpose. Okay. If you see that actually unwanted, what are the things, you can see that background. See background, it is not record actually. Background also going to have actually some storage actually, pixel it may get it actually. I do not want actually this uninterested. This one actually background actually I am not interested actually. Okay, as well as actually look at here actually, you take it this image I want to store it. Kind of image compressing. For that also one can use the principal component analysis. So now you take it this picture actually for to actually to save this picture actually we do not need actually all the pixel. For example, if you take it actually forehead if you are taking actually no, for example forehead actually the original figure it is maybe actually 10 into 10 pixel. Forehead is 10 into 10 pixel. But if you see that actually forehead follows some pattern, forehead actually having actually some pattern, so no need of actually all the information of the forehead. Okay, see if you are able to do it here actually, suppose 1/3 of this above pixel it is enough for extracting the picture, then actually we can save our we can save our storage space also. Okay. So this also actually another thing, we do not want to actually keep it actually all the original data. We can actually one-third of pixel if I know, I can get it actually forehead. Okay, I can retain the forehead in the image actually to save the image. Similarly, if you take it as sick, if you are taking sick also following some pattern, no need of actually complete information about the sick. Okay, for that actually if you are actually reducing the size, maybe 1/2 pixel also out of original pixel actually 1/2. Okay, so out of original pixel maybe 5 cross 5 pixel for storing the cheek of this person. If I am reducing actually 1/2 pixel only, it is enough. Half of the original pixel it's enough for storing the image. Then we can have actually save storage space. Okay, so this also actually one can use the principal component analysis to save that the original image in without actually compromising the quality And also in the less storage space also one can save it by using the principal component analysis. What principal component analysis is doing here, it's unwanted actually things it is actually removing. And also if something is following some object or some feature following same pattern, see it will not take actually complete pixel, it will take actually record pixel only, it will take it save. That also principal component analysis is doing here. Okay, so mainly here if you want to save this picture, mainly one can look at actually maybe the cheek, maybe forehead, maybe eyes and nose. Okay, some more things. Generally these are all the important things. Generally we used to call actually, this is in the machine learning term is called actually features. I don't know much about actually machine learning. Mathematical, I'm trying to explain some fundamentals. Actually, I'm trying to tell about actually principal component analysis. Okay, so it is enough to consider cheek, forehead, eye, nose, and some ear. Okay, these are all things enough to consider. And also we used to look at actually some pattern following this kind of things. If I are following, then actually we'll take it as that small information. If it is following some pattern, we'll take it actually try to actually keep it less pixel to retain the original things. Okay, that one done by the principal component analysis. Okay, so these are all the actually kind of motivation exactly what principal component analysis are doing. So quickly I can review actually what principal component analysis is doing. One is actually higher dimensional data can be reduced into the lower dimensional data by using the principal component analysis. The second thing is that compressing, one can use the principal component analysis. Mainly it's correlated things are removing the principal component analysis. If you do this thing actually, already I told that one can save the storage base in the second example. The previous example also same thing. Lower dimensional, if you are reducing, that storage base of actually the data will be less, and also the machine will do the things fast. Some accuracy also. Okay, so computational time of actually understanding the data also very easy. For us also some higher dimensional data is given. One can actually reduce into the 2-dimensional, 3-dimensional. Then actually human can easily visualize the data. Okay, that is a main motivation of why we need to do the principal component analysis. Okay, so now I'm coming to the mathematics the behind the principal component analysis. Then exactly actually how one can actually find that principal component. Okay, is it clear? Actually, anyone have any query, you can ask me. See, my task is now. Yeah, my task is to how to reduce the higher dimensional data into the lower dimensional data. What kind of mathematics behind that, and also mainly how I can compute this the principal component axis. Okay, from here you can get the idea. Only it is nothing but kind of projection map. We'll take the data actually, then actually we'll project into the some line. Okay, that line, how will you find it? That is actually very important. And also once you are projecting second principal component, also won't have to find it. You will project the data onto the second line, which is R to the previous principal component axis. Right. So okay, now coming to actually what is exactly mathematics, how one can find the principal component axis. Anyone have any query so far? Right. There is.
Excuse me, sir.
There is no. Yes. Yeah.
So there is a question posted in the chat box. What
yes.
about for scattered data?
So what about the scattered data? So scattered data
Yes,
also
sir.
same thing, one can do it. Yeah, scattered data also the same thing, one can do it actually. But at least in that case, still one can find the principal component analysis. We need to check it actually. One dimension less also if you are doing, that is success only. Okay, the scattered data also I am not sure. I'm sure that actually some error always will be there. See, scattered data is there, still one can find the kind of actually it's a new coordinate system. Already actually that is a example, x and y are actually axis. One can always find the u1 and u2. That is nothing but actually axes which are orthogonal. Always one can find it. One can find it, but actually that will retain our original data or not. We need to do actually some error analysis. Okay, but in the actually the scatter data case, actually, if you are reducing one dimension also, that is our success only. Okay, so I will explain actually the scatter data. Still one can take it. Same thing one can do it actually. Same thing one can do it. I will explain actually how we are doing that, how we are finding the principal component. Okay, mainly we are trying to reduce into the projection when you are doing now. When we are doing the projection, that length actually we are trying to reduce it. Okay, right. So I will tell, I will come to you little later. You can understand scatter data. We need to check it actually whether the two-dimensional, once you are reducing into the two-dimensional, whether this is going to give actually, whether it is going to get almost all the information about the original data or not. We have to check it. If it is not giving, we have to increase the component, the axis we have to increase. 3 components we have to take it. Then tell actually, then look at actually this is going to give the almost actually original data or not. Okay, always some error will be there. Okay, so later actually you can understand, right? So I will tell how we set the projection axis. Okay, that is a main important thing actually here, that I am going to explain that how one can set the projection axis. Okay, so that I am going to explain it. Okay, any other question? Is it okay? What about the scatter data? We are finding actually one coordinate system to another coordinate system. We are actually moving. Okay, so right. Okay, I'm coming to next one. Anyway, it is taking too much time. Right. So, see here actually it is very clearly actually what that is actually participant asked. That is exactly our main task is that how one can find that is projection axis or principal component. I'm calling actually the principal component axis. Principal component axis, right? Right. So now actually what I can do actually, first you take it this one, consider the set of points. Suppose I'm going to find how one can find the W. It's very clearly actually the W is nothing but the projection of the data points. Okay, the projection of the data point, and also where you are projecting in that line, you need to get actually the variance is greater variance, you have to get it. That is a very important thing. Look at here, you cannot fix this line you are fixing now. How I am fixing this one? I am getting actually greater variance in this direction. That is must be the first principal component. Okay, so because of this data varies from here, it is coming. So I am getting actually the greatest variance in this direction. Okay, that is going to be first principal component. Second principal component is nothing but, again you have to look at actually that line which is perpendicular to the first principal component. In that you need to get actually the greatest variance. Okay, after the first principal component, you have to get a second, the greatest variance, which through the which axis it is happening. That is I am calling actually second principal component. Okay, so anyway, this is what I want to do it actually. The consider actually data, consider the set, consider the data set, consider the data set. I'm having actually x1, x2, xn, x2, xn in r power of p. Okay, anyway, this is actually n set of points we are having, that is in rp. Okay, so I want to actually, this is the data. Okay, I'm having this one. One can denote it in the data matrix also. I will come to little later actually. So x1, x2, xn is a point in rp. Right, r power of p. Want to actually find the what is a projection axis or first principal component. Okay, the first principal component of this point. For this point actually I want to find it. Okay. So what is actually what we are doing in the previous case, we are having the data point, then we need to find actually u1. So previously the example is very explicit, that's only we are able to try it. But some arbitrary things is given, we need to find actually what is the that is a projection line. Okay. So right. So is it clear actually what I'm trying to tell? Actually, we are having this again. I'm telling this one. It is a little bit. So I'm having actually this line. I want to find it. In that one, I need to get actually this the variance, greatest variance of the data actually in this direction. And also I want to get it. I want to minimize this projection. Minimize the whatever actually the points I'm having here. I want to project on this line. And also I want to minimize this distance, kind of least square. Okay, I want to minimize this one also. Whenever you are minimizing this one, then automatically the greatest variance also you are going to get it, right? Right. So here actually how I am going to suppose let W in RP, okay, that is actually in elements such that I am taking norm of W is equal to 1, I am taking unit vector. So I want to check it actually what kind of W I need to choose, that we need to find it. Okay, so just I am assuming let W, you are projecting this one such a way that actually I want to minimize this distance also, distance between you are projecting. Say x1 you are having this is a line W, your x1 is projecting on the W. I want to minimize actually the norm of x1 minus this point wherever you are projecting actually, that is W prime. Okay, maybe the W1. I want to minimize this distance also. Okay, so minimization also it's required. So what I'm telling actually W is we are projecting xy, xi is projecting. I want to find what is a W explicitly. Xi is projecting on W. Okay, what will be the vector we are going to get it? The simple linear algebra. If I'm projecting x1 on the line W, then what will be the projection point? What is a point this one? Little faster I will see here. You can say that actually projection of x on W. See what I am going to xi. See what you are going to get it. Anyone have an idea? That is going to get actually xi into W into W. Will you agree this one? So this is a point. Whatever I am getting, that is generally xi comma W. W. So geometrically we'll try to understand. When you are projecting this one, this is going to actually this sitting on the line W. So it is going to be alpha time into W. That alpha one can evaluate it. The alpha is nothing but actually this is a vector. This is a projection of xi on W. This is the vector you will get it, right? So what I want to do it actually, I want to minimize the distance also. I want to actually minimize the distance. Okay, the distance between what? Distance between xi and this one, xi and this vector, projection vector. Okay, so we'll try to, the problem will become actually minimizing. Sorry. See anywhere if you are not getting, you can tell me. So minimizing, say norm of xi minus inner product of xi comma W into W. Okay, that I want to actually minimize it. So what I'm going to get it here, you can actually see this one. Not only actually one single one, I want to minimize actually in all the points. All the points I'm getting one projection, x1 having one projection, x2 I'm having one projection. So this distance, look at here, the distance between x1 and projection point will be this one, right? The distance between x1 and the projection point in W, that will be actually xi minus inner product of xi with W into W. So this one I want to minimize it. Not only one single point, all the point. So I will take it actually combinedly. So this is squared. Okay, this is a summation, minimize. Okay, better combinedly I want to do the minimization. Otherwise, simply one time you can calculate it actually. See, I want to minimize it. You just will evaluate what we are going to get it. You can actually xi with inner product of xi with W. So this is if you are doing just simple calculation, I will write it. We will not spend much time on actually evaluation. This simple evaluation only. So xi minus inner product of xi comma w into w. Okay, if I evaluate it actually, after simplifying, one can get it actually inner product of xi comma xi, okay, minus here I'm going to get inner product of w comma xi squared. I will get it. So this is simply a calculation only after simplifying. This is not a difficult thing. So I'm getting this one. Okay. So I want to actually mainly minimizing this one. I cannot see if you are not minimizing, that is not going to get actually greatest variance. Okay, it's kind of as a scatter data actually. This cannot be a the compound principal component axis. Okay, so this is I'm getting. I would like to actually minimize this one. So now we take it actually. So one more thing also I have to assume here actually. You take it. This data is given with 0 mean. That is also I will. For simplicity, I am taking actually with 0 mean. That is a record actually. If it is not 0 mean, one can actually make it as a 0 mean. X1, X2, Xn actually that is with the 0 mean. Okay. So otherwise one can find actually that average one can find it, then subtract it. New data you will get it. That is going to get as a 0 mean. And also at the same time, the translating the data, we may not lose actually much information. Even actually we may not lose any information. This is 0 mean. Data is given actually with the 0 mean. Right. So now actually you try to find actually this is I have to evaluate. I have evaluated as a distance between xi and the projection point. I want to minimize actually this one. For that combinedly I am taking this one, minimize. All right, here I am having. So this is actually now I will evaluate it 1 divided by n. The norm of it's not record actually 1 divided by n, but this is w. I want to minimize combinedly because all the distance I have taken between the given point and the projection point, I want to combinedly, I want to minimization. I is running from 1 to n. Okay. So this is one can evaluate it. What you are going to get already I have done actually this one. So this is nothing but norm of xi squared. Okay. Inner product between w and xi. So now if I evaluate this one, what I'm going to get it here, I'm going to get actually 1 by n time into the previous one, the summation of norm of xi squared, I is running from 1 to n, okay, minus what I'm going to get it here actually second one, I'm having actually the summation w comma xi squared, I is running from 1 to n, I'm having. See, mainly what I'm trying to do actually, I am trying to find actually what is a w. What is a w actually I want to find it. So this is I'm getting. So now actually you can, I want to minimize this one actually. Look at here, I want to minimize the distance between the given point and the first principal component axis. So now if I want to minimize it, look at this term. If I want to, I cannot do it anything on the xi because that is a given point. That's a fixed one. That is a fixed one. Okay, here actually w is only the constraint. The w only we want to find it. Okay, for that, if I want to minimize it, it's very clearly we need to minimize this one. Look at here, I want to minimize these things. I want to minimize this thing. The first value is actually fixed one, given point, that comes from the given point. Second one only we are having actually w. Okay, w only explicitly we want to find it. So only we need to actually, so in that case actually what we need to do, if you want to minimize it, I'm having the minus sign here. So I need to maximize the things. I need to actually maximize this one. So now we'll see how to maximize this one. Okay. I want to actually maximize this one. So one more thing actually one can write it actually this one. Look at here, this is a recall. Recall that. So variance, all of us we know actually what is a variance generally. Recall this one, the variance of suppose actually data yi, that is nothing but the summation of yi squared minus the summation of yi divided by n squared. This is suppose I'm having actually y1 and sorry y I am having actually y is nothing but point actually y1, y2, yn. Okay, so variance, the variance generally, this is actually we know actually the variance of the n data points will be the summation of yi squared yi squared minus summation of yi divided by n, average, this average of yi whole square. Okay. So now look at this term, how it's look like. Now look at actually that 1 divided by, now mainly I want to ask variance of the way this one actually, the summation I'm having now. So actually I will start quickly. Fundamental I may not. Right. So now actually what I'm telling actually is look at this one, from this one I can write 1 divided by n. The summation of I is running from 1 to n. That last term I'm writing xi square. Okay. So that is nothing but it is look like actually this term. It's look like this term actually that that is equal to variance of y plus summation of yi divided by n. Okay. So this what I'm going to get actually 1 by n. Here actually 1 by n. The summation of I is running from 1 to n. Inner product of xi with w squared. Sorry, whole square. So anywhere, suppose actually any mistake is there, you can tell me, because this is actually whole square, total square plus the variance of inner product of w comma xi. So this is what actually we are getting. So this is generally you look at here. Please, you can some time actually one can take it actually try to variance. I'm having this one. See here the points are given actually the w1 inner product of w comma x1, it is a one, the scalar. Okay. So inner product of w comma x2 also, that is a scalar. The inner product w comma xn also scalar. So now look at, see the actually the variance of this point. Okay. So see the actually variance of this point. I'm going to get actually this one. Okay, you can one can verify it. Right. Right. So mainly actually what I want to do it actually, again I'm recalling, we may not, there's a lot of the fundamentals we are discussing. So we have to keep our main goal is that I want to reduce actually this residual error. Okay. For that, if you want to minimize it, this one, okay, we need to maximize this one. Okay. We need to actually maximize this one. Okay. Maximize actually this one. Okay, for that actually I have written actually that second term is actually I have written actually in that way. Second term is I have written actually in that way. So one can see this one. One can see this one actually. Since x1, x2, xn actually the mean is 0. x1, x2, xn is mean is 0. One can see that actually the inner product of x comma w also mean is going to be 0. Will you agree this one? Okay, look at here actually I know that actually the mean of x1, x2, xn, that is actually 0. So this also going to get actually the mean is actually this kind of actually mean 1 divided by n into this one actually the mean also we will get actually 0 only. Okay, we can check it. Right, this also going to be 0 only, since the mean of x1, x2, xn is 0. By using that one can show this also mean is 0. Right. So this implies that what I'm getting actually 1 divided by n, that is I am looking in that way. So 1 by n inner product of w comma xi squared, that is equal to the variance of inner product w comma xi. Okay, right. So the second term is nothing but actually the variance of the data inner product of w comma xi. Okay, that's what actually we have control. If you want to maximize this one, we have to maximize the variance. Okay, here actually we are having one relation. Anyway, this. Anyway, So this is the one relation we are getting. Now I say anyway, directly I will try to see this one. I'm not able to see my arrow basically. Yeah, this is right. So now actually this one actually how I can write it, just evaluate this one. You can this is a variance only now. So we can take it actually the W of x squared. One can denote actually this one is I'm denoting sigma of variance of this one. Just I'm taking sigma squared of W. Okay, this is actually I'm just notation only. I'm getting 1 by n. The summation of I is running from 1 to n. Inner product of W comma xi w this one. Okay. So just try to actually will evaluate this one. Try to evaluate this one. What I'm going to get is actually just you can. So this is a summation I'm having. Just if you are rewriting this one, I'm going to get actually 1 by n into xw transpose into xw. So this W and so this is if you want to write in terms of inner product also one can write it. So this I'm having actually summation runnings from the W to xi. Okay, W to xi you are having. So that one can write it. So this is x1, x2, xn I'm having. This is I am having actually the p cross n. One can take it the matrix x equal to. It's a little bit lengthy calculation. Here I am writing. Suppose you take it here, one can look at x. I am taking actually x1, x2, xn. Okay, this is a matrix of size is p cross n. Okay, so w into xi. What is this? This one you can calculate it x time into w. X is a matrix. W is a vector in. I know that w is a vector in Rp. Okay, so x into w. What I am going to get actually this is nothing but actually. This I will get it inner product of I think better actually will take it x transpose into w. This is actually x transpose right. So this is actually how I can write it. See inner product of w into xi. Okay, so it's look like I hope that I have to take it. This is it's not actually correct order. It's not actually correct order. I will take it in that way. See, you take it x1, x2, xn. Now it is fine, I think. So this is order actually n cross p. Now actually w is one can do it. Now you can multiply actually w in Rp. So xw, x into w is nothing but you are going to get inner product of xi comma w. So here actually x2 comma w and so on xn comma w. Okay, that's what actually here you are having actually squared. You are having actually squared. So one can take it actually this is nothing but actually this is actually x term w. So can I write it actually this w comma xi squared is nothing but I would like to write it in that way 1 by 2 time into so look at sir 1 by n time into xw transpose into xw transpose. Will you agree this one? Because already xw already I told this one. Okay, xw I have mentioned that x is a vector is n x is a matrix of size is n cross p. W is a vector in Rp. So xw is nothing but one can think about actually the first row into w that I am writing inner product of x comma w like that. Now xw into xw transpose if you are taking that is I am going to get summation of I1 to n. This is you will get it right. So it's very clear only. So this is I am getting okay, anyway. See anywhere computation is not clear you can ask me because of very less time we cannot do much actually. So finally that you are going to get 1 by n into W transpose X transpose X W I am getting. So that is nothing but the W transpose into X transpose X divided by N into W. So look at here, I say this is what actually we have derived. Okay, so sigma here, sigma W squared. I want to maximize this one. See, we want to actually maximize this one. That one actually finally we are getting actually sigma squared W. That is nothing but the W transpose of this matrix. Okay, this matrix I will take it B time into W. So B is nothing but X transpose X divided by N. Okay, so you can one can check it actually. This B is going to get actually the covariance matrix of. Anyway, I'm not going to do it. So you can verify it. We have less time only. So B is a covariance matrix of that given data X. Okay, the covariant matrix of actually X. Okay, one can compute it actually. So this is one can check it. Anyway, that is a different thing actually. That one can verify it. So finally, what I'm getting actually sigma X squared is nothing but B time into W transpose into BW. This is a quadratic form. Quadratic form. See, when we are going to get maximum, the quadratic form of a W is a unit vector. The quadratic form of B is, look at actually B has some special property. B is symmetric, and also P is actually positive. Definite you are going to get actually anyway positive, semi-definite I am writing right now. The positive semi-definite, one can check it. So all the time is clear, it's fine. Otherwise you can ask in the last. P is a positive semi-definite, and all the eigenvalues of B is greater than or equal to 0. These are all that the properties of B here. When a covariance matrix is always a positive semi-definite matrix, a symmetrical is positive semi-definite, all the eigenvalues of B is greater than or equal to 0. See, now actually matrix theory, we have one result actually. Whenever A is a symmetric matrix, this is a result. One can prove using the optimization. Okay, so that I may not prove it now. The result is that whenever A is a symmetric matrix, okay, so the maximum of X transpose AX, okay, where norm of X equal to 1, that is going to get actually maximum eigenvalue of A. So that is a result. Similarly, the minimum, if you are taking the quadratic form, minimum of the quadratic form of A, the minimization over actually that norm of X equal to 1, that's you are going to get the minimum eigenvalue of, you take it actually the minimum of all the eigenvalues of A. So that is actually, that is a result. Okay, now tell me what then, and also one more thing is also understood. Where you are getting the maximum, the corresponding X is going to be eigenvector. Okay, so you will get actually, this is a result in matrix theory. One can use that, the fundamental optimization actually one can prove it. Anyway, I may not prove it now actually. I'm planning to prove, but it's taking too much time. You can take it. The result is this one. See, where you are obtaining the maximum, okay, there you are going to get lambda. Which point you are going to get the maximum, that is going to be corresponding eigenvector. Okay, so corresponding eigenvector you are going to get it. So Ax equal to lambda 1x. Okay, so lambda 1 is going to be, these are all the eigenvalues if you are taking, then X will be the eigenvector. That's what I am. Where you are getting the maximum value occur, that X is going to be a corresponding eigenvector. Right. See, similarly here actually, minimum of this one quadratic form if you are taking, you will get the minimum eigenvalue, you will get it. Where you are getting the minimum eigenvalue, the corresponding X will be the eigenvector corresponding to the minimum eigenvalue. Okay, this is a result in matrix theory. Right. So now actually already the people asked actually how one can find the W. What is a W? Okay. So how one can find the first principal component. Here what is tell, I say what is telling here actually, look at here, P is a symmetric matrix. I want to make it actually sigma W squared is maximum. So sigma W squared actually maximum if I want actually, where I am going to get actually maximum, I am going to get maximum at a point at a vector W, and what is the maximum? The corresponding, the largest eigenvalues of B. Okay. Where I am going to get the maximum, the largest eigenvalues of B, I will get the maximum, I will get it. What will be the where you are going to get maximum? The vector, that vector will be eigenvalues, eigenvector corresponding to W. Okay. So this is the conclusion actually I want to make it here. So here W will be, if you are applying this one, then I can conclude this one. So maximum of sigma W squared, that is going to maximum of the W transpose P W, norm of W is equal to 1, okay, occurs at actually that eigenvector W of lambda 1. Okay, so that is actually eigenspectrum of this one. This is the largest eigenvalues of B. Okay, so now actually you may get some idea how one can find the first principal component. Right. So I'm giving some time. Actually, you can think about, anyone have any query, you can ask me. So this is the things we would like to find the principal component where I want to actually the project. Okay, such a way that in the direction of the principal component, the greatest variance you will get it. The greatest variance of the data set you will get in the first principal component. Okay, so that W is nothing but here you have to find actually the B. Okay, B is nothing but covariance matrix of the given data. Okay, now look at actually the largest eigenvalue you have to find for B, and look at actually corresponding eigenvector. You have to look at actually corresponding eigenvector. Actually, you have to look at that is going to be a first principal component. Is it clear actually? So how one can find the first principal component. Similarly, second principal component, if you want to find it, the same thing we have to do it actually. In that case, actually, you have to remove that one, the W, the span of W, you have to remove it. The span of actually this, once you are fixing the first principal component, the second principal component, if you want to find it, you have to actually exclude the W, then actually do the projection on n-1 dimension, which means orthogonal to the subspace spanned by W. Okay, in that one you will get the maximum. You will get actually the maximum eigenvalue for the B restricted map on the orthogonal complement. Okay, that corresponding vector you may be able to find it. That will be the second principal component. Okay, in which actually second largest eigenvalue exists. Okay, otherwise simply I can say that the second largest eigenvalues of B, the corresponding eigenvector will be the second principal component. Okay, this is the conclusion. Okay, I will do one problem. It will be very clear. So, anyone have any query so far? Okay, anyway, quickly I can, maybe a lot of things we have done actually. So, I have started with some data set actually x1, x2, xn in RP. Okay, right. So with zero mean, we are having actually mean if you are taking that, you are going to have actually zero mean you are having. I would like to find actually what is the principal component, what is the line I have to choose such a way that you will get the greatest variance, the direction of the greatest variance in the projection line. Okay, that is a very important actually. We would like to find actually the line, projection line, in which your data set having the greatest variance. Okay, that is equivalent to you do the projection of a projection of all the points on the line and find the minimum. You try to actually minimize the error. You try to find the minimizing the error. Okay, that is actually going to give actually the line in which the data set having the greatest variance. Okay, the final conclusion is that your W is nothing but you have to find the correlation matrix of covariance matrix of this one, okay, covariance matrix of this x1, x2, we have to find it. Then find the largest eigenvalue of the correlation covariant matrix and corresponding eigenvector. That will be the first principal component. The second eigenvalue of covariant matrix and the corresponding eigenvector will be the second principal component. Okay, so that is the thing actually. So I will do. Anyway, I cannot write it all those things. Fine. Okay. So I will come to actually then now what one can do it actually quickly. I will tell what is actually step by step what we need to do it. So a few more important things also I have to discuss here. Suppose I'm having the point actually. This is a given set. Consider this data set. I hope that theory you have understand. Let me quickly I can step by step what we need to do it actually. Suppose I have the data set like that actually. X1. X2, you are having actually XP. Okay, so this is a matrix X. It's a matrix X actually. This one can take it as a this is going to P cross N. Okay, which means all the X is in R. So this is actually the data matrix. So this is a data matrix actually, or actually data set is given this one. Okay, we are having, or one can think about actually endpoints given in the RP. Endpoints given in RP. Okay, so here one can think about actually endpoints given in the Euclidean space RP. Okay. So now what we need to do actually step one, we need to find. Anyway, we do not know actually mean is 0 or not. We do not know for this data. For that actually, I will actually find the mean of this one. So mean I will get it actually 1 divided by n data set I'm having, the summation of yeah, this I will do it actually summation of right. So summation of I need to do actually x bar will be a x bar of better I will take it actually this is going to get actually x bar will be the summation of x this okay. So this is actually that mean we need to take it actually because I want to make it whatever theory we have done that is for actually zero mean. Now consider this one actually x minus x bar. Okay, that is a matrix whose size is going to get P cross N. Okay, that is a matrix. I will take it actually some C. Okay, C is a matrix actually x minus x bar. Okay, this size is actually going to be the size of the matrix is this one. I will do x minus this common. Each place actually I will do this one. Okay, x minus x bar. Okay, this is a matrix I am getting. Now I need to, this will become actually the zero mean data or actually that mean centering data. Otherwise one can actually mean centering data. Mean centering data you will get it. Right. So now actually where you want to project actually this is for this one only I want to find the principal component axis I want to find it. For the previous discussion what you have understand actually the first component is nothing but the covariant matrix of x minus x bar. Okay, the covariant matrix of x minus x bar, that is nothing but actually you have to take it actually C transpose C. Okay, you have to take it actually the sorry CC transpose. I think actually this is going to get actually CC transpose. CCC transpose. Previously we have taken the data as actually column we have taken. In that case we have taken data as actually row only. That's only as a CC transpose. Anyway, 1 divided by you have to take it. This how many data are you are having? N minus 1. Anyway, this n minus 1 is not matter actually. So this is you have to take it as B. This is going to be a covariance matrix. Okay, so here actually why we are divided by n minus 1, the reason is that this data taken from the population, when you are finding actually that variance, we need to divide it by 1 divided by n minus 1. One data is less. Okay, so this is a sample data, that's only we are doing actually. The previous case, the population, that is n itself we are taking. One time you can go through actually, whenever you are finding the variance for sample taken from the population, we will do 1 divided by n minus 1. Okay, that's a Bessel correlation generally we used to call actually. This is actually 1 divided by n minus, but this is not a matter actually. This coefficient, this 1 divided by n minus 1 is not a matter. Okay, right. So CC transpose is going to be a covariant matrix of X minus X transpose. Now you will evaluate that. You try to evaluate it. All the eigenvalues of the step 3 will be find all the eigenvalues of of B. Okay, so generally this is a symmetric matrix. B is a symmetric matrix. What I am going to get here actually, all the eigenvalues are real. So one can write it any symmetric matrix the orthogonally diagonalizable. Okay, so as B is a symmetric matrix, B is symmetric. Okay, so there exists a orthogonal matrix B such that the D also I am taking the lambda 1 0 0 0 0 0. Okay, so lambda 2 and so on. So this is going to get actually P cross P matrix. This is actually you are having P cross N. This is N cross N. This is going to be actually P cross P matrix, the square matrix. So this D is a matrix with I am having this order lambda 1, lambda 2, lambda n. Okay. So in that case actually you are going to get matrix B. One can write it actually the P transpose B is nothing but the diagonal lambda 1 0 0 0 lambda 2 0 and so on 0 0 lambda P you will get it, right? So this is the spectral decomposition of the symmetric matrices. See, these are all the things one can do easily computation. It's not an issue. Here main thing I want to take actually what will be the first principal component, what will be the second principal component. Okay, that is I want to find it. Already the previous discussion we can understand what about actually the eigen, the P one can write it, the P1, the P2, this is a column of P. See, these are actually the columns of P. Columns of P. Okay. So in that case, P1 will be the first principal component because of I have taken lambda 1 is the largest eigenvalue and P2 will be the second principal component and so on. So in that case actually I have, I think this is PP. This is a PP. Anyway, this notation is some same P I am using, so it's understood. So PP will be the Pth principal component axis. So here mainly we are actually rotating the data. The orthogonally we are rotating the data such a way that the greatest variance sitting on the first principal axis and the second greatest variance going to sit on the near to the second principal component. Okay, that's what we are doing. So here mainly where we are reducing the dimension. That is a question. That is where we are reducing the dimension. I'm having actually that is RP only. I'm having the point again. Actually, you are projecting in the you are having actually the P axis you are having. Then where you are looking the lower dimensional data. Okay, that is maybe the natural question. I have that actually data in the R power of P, Euclidean space R power of P. Again, I'm going to get denoting the data in the R power of P only. There is not much interesting, you may ask. But here, what we are going to do here, that is a very crucial thing. We have to look at this one. Whenever I say the P1, the here now the P1 actually going to have actually that only the P1 actually going to give actually the larger information about the original data. Only if you are keeping on actually P1, that will go actually, it will retain the almost all the original information about the data. Next one actually P2 is, if you are adding, it is going to accuracy going to increase. Okay, accuracy of actually the data, original data is going to increase it only if you are considering P1 and B2. Okay, you are projecting only the P1 and B2, your data will be denoted by only the two tables. If you are considering P1, P2, P3, your data is going to consider as a three-dimensional data. Okay, but up to how much dimensional data if you are projecting, which is going to give actually accurate answer. Accurate meaning actually the error is less. That is maybe a question, right? So here actually this is the thing, the total variance, generally the total variance actually one can denote it by actually the trace of this matrix actually, what I am taking P, I have taken trace of actually B. The trace of B will be the total variation because of each the diagonal if you are looking, that is giving the variance of X, variance of the first random variable. Second one is the variance of the second one. A kind of random variable only generally probability theory statistics used to talk about a random variable. The third diagonal index related to the third variable actually. So each variance actually sitting on the diagonal, if we take the sum, we are going to get actually total variance of the data x1, x2, xn. Here in that case, x1 minus x bar, x2 minus x bar, and so on. So this is going to be a total variance. We know the relation between the eigenvalues and the sum of the diagonal. That is going to be lambda 1, lambda 2, and so on, lambda p. Okay, this is sum of the eigenvalue. Okay, so now actually coming to this one, up to how many projection we need to take it. Okay, which means up to how many component we will take. If we taking, we will get actually that almost all the original information will be retained. Okay, so this is the things one has to check it. I may not do error analysis. What we need to check it actually, we have to calculate it lambda 1 divided by summation of. You have to check this one. The lambda 1 divided by the summation of lambda I is running from 1 to P. Okay, you have to look at this ratio. If you are getting actually, this is actually 0.95 or something, it will get it actually. This is a lambda 1 is largest, automatically you are going to get actually this point is that is actually near to 1. If you are getting, then it is enough to take it only the first component. Even no need of actually second component. So yeah, that is some important things I would like to tell here. You may have actually question on that. How many principal component if I consider, I will get the almost all the information about the data. Okay, so now once you are finding all those things, lambda 1 divided by summation of I1 to P, lambda you calculate it. If I am getting this one 9 or 9.2 or 0.85, something you may get it. So this is what is telling this one actually, you are getting actually the 90% of the data actually you are retaining only considering the first component. Okay, if you are getting 92, meaning 92% of data, you will get it only considering the first component, right? So please, I am not writing here actually. If this means that actually only taking one-dimensional data, first component. So you are projecting into the only the first component axis now. That one-dimensional data itself going to retain the 90% of the data of the original one. Okay, right? So only error will be actually what is actually 5% only will the error. Okay, that is depending upon situation whether we need to add a second principal component or not. Suppose once you are not satisfied, you are considering only, you are reducing the higher dimension only the single dimensional. If you are not satisfied, I want actually more accuracy, then you consider higher dimensional data reducing to the two-dimensional data. For that, just evaluate lambda 1 plus lambda 2 divided by summation of lambda I1 to P. Okay, so what is the ratio? Automatically it will increase. right? Automatically it is going to increase actually. In that case, suppose you are getting actually 98 or something. If you are satisfied, which means that you are reducing the data into higher dimensional data into 2-dimensional, you can retain the data 90%, almost 90%. You can retain the data. Okay, so in that case, actually, you can fix according to your requirement. You can think about up to how many components you can consider. So main important thing is this one. Slowly you can increase it. But I say no need to go up to actually the last P. All the P components if you are considering, it's a waste only. Only maybe 1 or 2, 3 places you will get actually all the data one can retain. Okay. Anyway, I would like to do some example. Anyone want actually example? I will do it. Otherwise, I can stop discussion. Right. So this is a conclusion is that in that way actually one can actually fix how many components one has to consider. Okay, that is depend upon actually your requirement. Right? So I will stop discussion because a lot of things are there. In this class, in this talk actually mainly I given actually minimum information about how one can actually find the principal component axis. Okay, then what kind of actual application of the principal component analysis. Okay, so I will stop discussion. Anyone want actually more? Then I will do actually some example. Okay. This is one of the fundamental thing actually. You can see that we are using the elementary things from the linear algebra. Maybe the optimization also can be done. Okay, that one result related to matrix I have written. That is one can use the optimization, the minimize the quadratic form. You will get largest eigenvalue and all those things. You will get it. That person I planning to do it, but due to the time constraint, I have not done actually. So anyone have any query, you can ask me. If you want something more, actually, I will do one example so that it will be very clear. Right. Yeah.
Participants are open for questions. So there is a question from Sarang.
Yes.
Shall I read it out, sir?
Yeah.
How we set projection axis?
Where is that? That I explained, ma'am. This right now. I hope that actually Sarang it's very clear to you how one can actually projection axis. That is nothing but I told actually you find the covariance matrix. In that one, what you are getting the largest eigenvalue, corresponding eigenvector going to give the first principal component axis. Okay, that is kind of projection axis, whatever your main meaning. Okay. Right.
Sir, another question from Sarang.
Yeah.
Why do we need variance?
Yeah. So variance actually mainly the data, whatever data we are taking, our main aim is to remove the correlated data. Because of the correlated data are there, actually it will disturb the complete things. Even it is not record also. One data is there, actually from there we can actually retain the information. But the data are correlated, there no meaning of actually taking the point. Mainly we want to remove the correlated actually from the considering the variance actually we are removing covariance matrix, all those things. Okay, so that is the main thing actually we need to consider the covariance matrix. We are removing the correlated data we are removing, only we are keeping the uncorrelated data, which means uncorrelated feature only we are keeping. Okay, that's only that dimension automatically is reducing. Right, is it fine?
Yes, sir.
See, any other question? I do not. Yeah.
Participants, if you have any other questions, you can raise the same.
If participants, mics are unmuted. If you ask anything, kindly unmute your mic and then speak.
See, even actually, I'm not actually that specialist in machine learning. I am actually also that beginners only. Mathematically, little bit I know background actually. But I'm not actually good in machine learning. Already I mentioned to the Pravina madam also.
Yes, sir. Yes, sir. Hope there are no questions from participant side. Okay, let me conclude then.
Yes,
We extend a sincere thanks to to Dr. R. Palpandi for delivering an informative session on mathematical foundations in AI, especially the principal component. Your expertise and perspectives have enriched our understanding, and we appreciate your time and effort in sharing your knowledge with us. Thank you once again, sir.
Yeah, thank you.
A big shout out to all the amazing participants of this session. Kudos for your active participation. Thanks for bringing in your perspectives and questions. We truly appreciate you all for being part of this knowledge sharing journey on AI and mathematics. Thank you all once again. A feedback link has been posted in the chat box. Participants, kindly fill the feedback form. The feedback link will be open for only 10 minutes. Participants can leave the meeting once you fill up the feedback form. Thank you all.
Okay. Yeah. Thank you so much, ma'am. We will. Yeah. Thank you once
Thank you,
again.
sir.
Thank you.
Thank you, sir.
Yeah. We'll see, ma'am. Okay. Thank you so much.
Yes, sir.
Okay. Yeah, thank you all the participants to listen patiently. I hope that any question is there, you can mathematically, you can ask, you can mail me also. Okay. Yeah. Thank you so much. I am leaving me.
Yes, sir. Thank you, sir.